There we go. Looks like we can get started. Welcome back, everyone. Kind of fun fact, everyone in class physically today is kind of arranged on a diagonal line. It's always an interesting pattern to see. Just randomly, that's how people fall, I guess. But welcome back, everyone. I'm pretty close to being done with the exam. I'm just on the last problem right now, working through grading our exams. That means on Friday morning, I'm pretty much just finalizing them, putting in grades, and uploading the results to Moodle. So you'll have those results right away. And the hard copies will be passed back on Monday's class. Aside from that, we also have quiz 3 due today. And what was I going to say about that? Oh, the thing I also wanted to mention about the exams, I'm giving your exam score as a fraction. You'll see it as a percentage in Moodle, but I'm also going to give you your grade up to how your grade stands on Friday morning. So that's going to be up to quiz number 3 and whatever section was due last in the math stats lab. Never get used to saying that. Looks like the last section due was sections 4 or chapter 3 right there. Hang on, let me take another look. No, it was chapter 4. Chapter 4 is going to be the last section due. This is due today. So when I give you your course score on the exam, it's only going to go up through that section there. As far as the other announcements, it will include quiz 3, like we mentioned. And also we have our 4th quiz already posted. So we're kind of just on the track of going through the weeks in this normal kind of pattern. Any questions at all, folks, at the moment? Okay, and we had a pretty lively discussion on this problem right here. I think this is one of the most trickiest, confusing problems in all statistics. When we're thinking about measures of position, measures of spread, it's one thing to label these out, but a whole other thing to show how they actually work with formulas. So let's jump back into the notes, continue on to that problem in example 2. Any questions or comments whatsoever first, folks?
This is 5.2 shifting and
Exactly, yeah. We're nearly done. I think we'll still spend a good amount of time in there because if that was a pretty confusing section, you ought to spend more time taking a look at it. And section 5.3 is a larger section. So I was intending that we'd probably finish this on Monday's class, possibly. So we'll make an early start on that section. So let's take a look. We left off right here. I posted the 2 theorems for shifting, rescaling the data, just to have it available as we read through these things. What we did was, we're looking at a study of 130 healthy men and women. They tell us that they found the mean temperature was 98.25 degrees Fahrenheit. I'm highlighting these things in blue. Let's just put blue on this just for emphasis, because that tells us we're talking about measures of position when we're looking at those statistics. We had the 96.3 degrees for the max. Oh, that's the minimum. 100 degrees, 0.8 degrees for the 100.8 degrees Fahrenheit for the max. Geez, feels like we're highlighting the whole problem. And we need to use that formula there to show what all of those 4 statistics will be if we were putting them in Celsius. So using the Celsius formula. Let's highlight that. Well, that might be kind of hard to read. Let's take that off. That's hard to read on my screen, at least. So the trouble with all this that we mentioned before is the original formula is just fine for ordinary operations. In fact, it's fine for measures of position. However, if you feed it this thing, the measure of spread, we immediately run into a problem. There's no harm in actually calculating it. You can put 0.73 degrees right here, multiply it by 5, or excuse me, subtract 32, multiply by 5/9. You'll get an answer. But it turns out it's not the right answer for standard deviation any longer. That's really super confusing. So before we go to example 3, I want to show an extra example, kind of bonus problem in the middle, that could explain this a little bit better. But for the moment, what we did was we took this formula, which is totally fine for most purposes, but not in this situation, and we had to distribute 5/9 through the group. So we had 5/9 times f, 5 times 32 is the negative 160, then divide by 9. And now looking at this where it says shifting the data, let me try this pen right here. Shifting the data is this portion. We're subtracting 160 after doing the multiplication right here. When we say rescaling the data, we're meaning this right here. So this portion is rescaling. Reading the theorem through once more, it says, if we shift the data or rescale the data, it's going to shift the data for all measures of position or rescale the data for all measures of position. That means these statistics highlighted in blue, we use the whole entire formula. But the one that goes a little bit awry is shifting the data for the measure of spread. The measure of spread is unchanged. Again, that's pretty wild on this. I don't want to completely undo that color coding on that, but it's definitely kind of strange how that works together. And there it is, that's our measure of spread. So when we go to use that right there, we only use the rescaling part because shifting it leaves it unchanged. And that's the shifting part of the whole formula. Lots going on with that problem, but does that make sense first on that initial look through?
Shifting in. Shifting only affects measures of position.
Exactly, yes.
Okay.
So that means this is the odd one out, unaffected.
So rescaling does the whole thing.
Exactly.
Okay.
So the 5/9 multiplying by the Fahrenheit temperature is going to affect everybody on that list. So let's go through it. I'm going to keep the color coding blue when we're looking at measure position, green when we're looking at a measure of spread, just to keep that correspondence separate in our mind. Our first one is the sample mean Y bar. Let me actually put that a little higher. It's 98.25 degrees. So what we would do is take, in this formula, 5/9, multiply it by 98.25, and subtract 169. So that's one down. And the calculator, it's kind of tricky to put in, but as far as order of operations go, you can kind of go linearly. So 5 divided by 9, just go 5 divide 9. Multiplying by 98.25 could go times 98.25. And the calculator is going to use order of operations correctly in the way we intended. It's going to divide first, then it's going to multiply, going left to right. Then subtract 169. Like we mentioned before, if you had these in as a decimal number, like 17.7 repeating with negative sign, that's just as good. I'm using the fraction. It's more of just a stylistic choice. You'll get the same answers. So in Celsius, this sample mean came out to 36.81. I'll go to 2 decimal places. Looks like I forgot to indicate that. So 36.81 degrees Celsius. So that's the game so far. But this is the odd one out. So let's be really careful with this one. The standard deviation S is a measure of variability or how spread out the data is. So when we go to use that, because it's a measure of spread, shifting the data leaves it totally unchanged. And that's the shifting part of the formula. That means for the moment, we don't care about that thing if we're considering S whatsoever. That is extremely weird. So again, I think that needs more explanation after we finish this problem. I have a little activity that we can do that can help justify that. But S is going to be, we take the formula 5/9, multiplied by the Fahrenheit value. This is 0.73 degrees. I guess the good news there is it's a faster computation. Here, let's go 5 divided by 9 times 0.73. And we get 0.41 degrees Celsius. So 2 down, 2 more to go. Any questions at the moment with those 2 statistics? Okay, once we got through that one again is the odd one out. We also want to find, let's see, the min and the max of the temperature values that were stated. But these both will use the entire formula, since those are measures of position. In fact, you could just use the original formula if you'd like at this point. You'll get the same values. So totally your call. In fact, let's use that original formula just to show how that would go if people would prefer it. So for the min, That's going to be equal to, actually, let's put that in blue, just to convey it's a measure position. The min is going to come out as 5/9. Using this formula, just to show how that different approach will go, we'll put in 96.3 degrees in that position, minus 32 degrees. So back in the calculator, another 5 divided by 9. This time a parenthesis to contain that whole group, 96.3 minus 32. So the min was 96.3 degrees Fahrenheit, and now in Celsius, 35.72 degrees. So 35, let me fix the 5 first. That 5 is not much better. 35.72 degrees Celsius. So last one to go, the maximum. So max, just scroll for a bit here, is going to be equal to, again, either formula is going to work. Let's use this one again. I think it's actually faster to use now that we're past the odd one out, this measure of spread. So we'll go 5/9, multiply it by the maximum temperature, 100.8 degrees. Sounds like an infection, probably, minus 32. Then just back here, it's sometimes kind of convenient to use what you already typed in, because you notice it's kind of tedious to type that in every single time. So some people might be doing things like this. You could up arrow, hit enter, left arrow, and just overwrite. You could put 100. Oh, not sure what I did there. Put in 100.8. And I'm kind of overwriting what I had before, but maybe it's kind of a small shortcut you could use there. So 5/9, so 100.8 minus 32 gives us 38.2 degrees Celsius. So that's the conclusion of that problem there. Any questions, folks, with running through those steps? Okay, again, this is a really shady theorem, this whole thing in total, where it says measures of spread are unchanged. That's what made this so unusual. The fact that we dumped part of the formula. You would almost never do that in a math setting, unless statistics are involved. That's when things get a little bit weird. So let's really show what's going on here. So let's put down quick border. Let's call this one a bonus example, because we're inventing it out of thin air. So let's say for this example, consider temperature measurements in Fahrenheit. Oh, I got it this time. I don't usually, I have to sound it out each time. In Fahrenheit from a sample. So let's just give a few of them. We don't want to get too wild. Just a really fast example. Let's say it's 32.8 degrees. Then maybe 49.2 degrees. Let's go 50.4 degrees. And how about an 11.3 degrees? Looks like an outlier in the data set. So we have 4 temperature values. Let's say for part A, find the mean and standard deviation. So pretty fast problem right there so far. In the calculator, we'll just import 4 values and crank out those statistics. So let's go stat, enter here. I only have 2 pieces of data, so it's just more efficient to type over them. So 32.8. Then next is 49.2. By the way, if you're typing over data, just make sure there's nothing down below in your list, since that will throw off your statistics. Then 50.4. And lastly, 11.3. So those are the data in. Next go stat, over to calculate, jam the enter key. And here's our mean, 35.925. So that's a measure of position, so I'll use blue there. Y bar is 35.925. And S's Always be careful with that one. Go for the SX. That one is to 2 decimal places, 18 point, oh, I guess we did 3 decimal places, so I'll keep the same. Rounded to 3 decimal places, 18.275. Forgot my unit, but I'll put it on the last one. The units for the mean and the standard deviation would always be the same. So that's kind of a quick hack to indicate units on both. So we have those nice values. And like we did before, we can use this formula to convert them. Let's say part B, find these values in Celsius. And let's put down the formula just for quick emphasis. Because this one's a measure position, we would use the full formula. So let's just do that one more time, see how it goes. So back to the calculator. Let me write it out just so that we see what we're actually computing. Y bar is going to be 5/9 multiplied by 35.925 minus 32. So that's a pretty fast computation. 5 divided by 9, 35.925 minus 32. And that's our value, 2.181 if we're rounding to 3 decimal places. Now, what about S? S, imagine you did the same exact step. So this would be a mistake. Probably don't write down the notebook. I'll use this red pen to convey it's not going to be correct. Let's intentionally make a mistake just to see what would happen. Because it really feels natural. Suppose you never took a statistics class. Someone says you have that formula, write out the mean in Celsius. No problem there. Forgot my unit on that. Degrees Celsius. Then you would just assume if you want the standard deviation in Celsius, take the same number, plug it in and get a value out. So let's just do that and see what happens. Again, this is wrong, so maybe don't write down the notebook. This is more of a demonstration. For the shortcut, I'll hit up arrow, enter, and we're just going to overwrite these values with the Celsius, 18.275. Double checking, it still says minus 30. Oh, what did I do? Sorry, I think double clicking is what's doing that. It still says minus 32, so we've got the right formula. And this comes in as negative 7.625. Already, that sounds weird, doesn't it? We have something going into negative degrees, but let's put that in. Negative 7.625 degrees Celsius. We have to ask ourselves, is that even accurate? That's kind of hard to tell. But there's another way to think about this. So let's go back to the calculator. This is the demonstration part where we would probably only ever do this one single time in class, just to show what's going wrong right here. Let's import our data, but let's do the conversion on every single data value and see what happens. Slightly tedious, but bear with me. This will be, take every one of these, plug it in for F. So that's why we only have 4 data values. So 5 divided by 9, parenthesis, 32.8 is the first one, minus 32. Then just hit enter, and that's our first conversion, 0.4 repeating. Do it again on this one, 40 for 49.2. So 5 divided by 9, multiplying 49.2 minus 32. Okay, so second value is at 9.5 degrees. That looks about right. So it went from 0.4 to 0.9 by increasing. Then 50.4, 5 divided by 9, 50.4 minus 32. Nearly there, folks. Appreciate your patience. That's really tedious to get in. These look about right. Then 11.3, one more time. 5 divided by 9, 11.3 minus 32. So this is like a hack. We're finding the standard deviation without actually putting the standard deviation in that formula. We're just actually rescaling, reshifting all the data itself and seeing what happens. So on the last value, we get a negative 11.5. So now let's go to the stat key. Let's go to calculate, one variable statistics, and see what we get out. Our sample mean is 2.181 upon rounding, same as that one. So we got the mean right. And look at our standard deviation, 10.1526. That's not only off, it's way off. That is extremely bonkers in a way, isn't it? A formula that you feel like should work just fine with some other number doesn't work on that number because it conveys the spread of the data. So if we really want to use the formula, we would have to eliminate this part. It's just 5/9 times f, and we get the right value. So let's see if we can land on that value we see in the calculator. I'll take a quick screenshot just for reference. Oh, and something weird happened there. Let me just move that off. So because this is a measure of spread, we delete the shifting part. I put the parenthesis just ending on f to say multiplying f by 5/9. And this is what we really need to do. Take 5/9, multiply by 18.275, and let's see what that comes out as. So 5 divided by 9, we're going to hate this formula after today, but we're getting through it. Multiply by 18.275. And this is our result. Comes out at 10.153 upon rounding. And that's exactly the value quoted in the calculator. So again, statistics are weird. It's the measures of spread that are always weird. They will not use the formula in the normal sense. So we always have to be extra careful. So this one is 10.153 degrees Celsius. Any questions, folks, with the weird things going on with the shift measures of position versus measures of spread? Okay, I think this is a fun problem in the sense that when you're doing it this way, there's a whole lot of trust that those theorems are true and real because we never even see the data. We just see the statistics. So I think seeing is believing. If you have the data, you can just convert everything and tell right away that formula doesn't actually work in full for the measure of spread, any measure of spread, whether it's the range, interquartile range, or the standard deviation like we worked here. So because that's a tricky enough concept, I planned ahead and already decided we should do another example on this. So this one was the bonus example. Just put this in red to convey, we put it in right after the fact. The class was already going on these notes. Now let's try this all out again with example 3. Any questions or comments so far? Okay, so another situation, and we've dealt with this before. We compared SAT scores and ACT scores using a z-score method, comparing standard deviations. But this one's giving us an alternate way to think about it. This is a convenient rule of thumb, they say. So it's not a perfect formula, but if you need to convert between ACT and SAT scores, that one does a pretty good job. At least that's what they're telling us here. I would trust them. They tell us here, each year, thousands of high school students take either SAT or ACT standardized tests in the college admissions process. Combined SAT math verbal scores go as high as 1,600, while maximum ACT composite score is 36. So it really is apples to oranges. It's hard to compare the two. They tell us next, since the two exams are use very different scales, comparisons of performances are difficult. It's just kind of unfortunate that those two are highly competitive exams. Can't just delete one. So we have that rule of thumb. Now it tells us next, an admissions officer reported the following statistics about ACT scores for a pretty large sample here, a sample size of 2,355 students who applied to her college 1 year. So here's the statistics given. For the measures of position, we'll highlight in blue. That's definitely going to be lowest score, mean, but like we saw before, standard deviation, that's a measure of spread. Anyone spot the other measure of spread on that list? Absolutely. The one on the very end is also a measure of spread. The two in the middle are also measures of position. So This form is a little bit easier to work with. In hindsight, probably should have done this one first because there's no distribute 5/9 through to kind of break down the formula. That semicolon just seems kind of awkward though. Let's delete that. So we can now say right here, this part, forget what colors we're going to use. Let's just use a generic comment pen. This is rescaling. And this part is shifting. So when we go to work out all of these, here's how it's going to go. Lowest score, I think it's more easily said as just minimum, would be equal to 40 times that ACT score, which was 19. And then question for the class, do we add the 150 or do we leave it off? Some say keep. I agree with the keep actually, because this is a measure of position. This shifting right by 150 would affect the minimum. The minimum is now going to increase by that amount after the multiplication. So we would convey that part. So plus 150. In fact, the only ones that don't use the 150 are these two. So for this one, SAT is 40 times ACT, and same for this. That's probably a good way to do this. Just write down the formula you need for the statistics, which are measures of spread, and use a slightly altered formula. But for the computation here, pretty fast, nicer numbers. 40 times 19 plus 150. So that gives us a minimum score of 910 on the SAT test. Does that make sense to folks so far?
The minimum score is 910?
910, yeah. On the SAT, that one goes up to 1600 is what they're saying. Does that make sense so far? Okay, let's try out another one. Yeah, our lowest was 19. The highest it could ever go is 36. But this score is 910 points on the SAT test now, not the SAT or ACT. Getting those mixed up. Too many acronyms on that. I don't even know what these acronyms even mean. We're just so used to saying them that it's like their own meaning as an acronym now. But that makes sense with the 910.
Yeah.
Awesome. So now moving down the line, let's go to the mean. You could just write mean if you prefer, but it's good to connect the dots that when you see mean, you're really thinking Y bar as well as a symbol. This will be 40 times the value of the mean, 27, plus 150. And here's where that shortcut again shines a lot in the calculator. Doesn't take much time to type that out, but if you up arrow twice, left arrow, and just put in 27, I think that's probably sort of faster, but it's more accurate. So that's even the bigger deal there. So 1230 points. Next is this dangerous one. Standard deviation is 3 here, but when we go to use that one, we're using that formula. It's going to be 40 times that ACT score's standard deviation. So S is going to turn into 40 times 3, and then that's it. That's the whole formula if we're dealing with a measure of spread. That's always weird. It never really made sense to me as a student in statistics when I took this. I just pressed the I believe button and got the question right. It's good to see why it makes sense, so I'm glad we did that short demonstration. This turns into the 120 points for standard deviation now on SAT test. So what we're saying here is these are statistics for the 2,355 students. But if we imagine they took the SAT instead of the ACT, that's the statistics on the SAT that we would have produced. So that's essentially what we're trying to convey by doing all these computations. Next up, quartile 3 is 30. So this will be equal to 40 times that ACT score, which is 30. But this time it's a measure of position, so we use the full formula. The shifting portion plus 150 has to go in. And this is not a hard one to calculate, but it's a Thursday on a night class, so let's treat ourselves to a calculator. I'm not the best at mental arithmetic, especially when it's late at night. So 1350 is the points for the third quartile. Now median, that one we usually write as a symbol M, is going to be equal to 40 times the score for the median, the 28, add 150. So kind of tedious once we see how it all goes, but reason for so many statistics is just so that we have to have that fight of which ones are position, which ones are spread. So up here, let's put in 28. And we get 1270. And finally, interquartile range. IQR is a dangerous one to use with these formulas because this one is also a measure of spread. It tells us how variable we are for the central 50%. So we use just this formula, 40 times 6. So take 40, multiply by the interquartile range, just a 6. 6 times 4 is 24, so this comes out as 240 points. And that means we did it, folks. That's the conclusion of this problem right here. Any questions at all on how this went down? Okay, when you go to do this on the MyStats lab, same kind of issues are going to come up. I don't think they're going to give you as many statistics, so the problems are a little bit shorter, but they're going to give you measures of position, they'll give you measures of spread, and so you have to decide what part of the formula am I actually going to use for each one of these. If this strategy looks like it helps, look for the measure of spread. Those are the weird ones, and just rewrite the formula for those, and you'll be on the right track. Well, we did it, folks. That's the conclusion of section 5.2. Chapter 5 has been weird so far. We've done z-scores. We took a whole nother look at our statistics and saw how they interact with formulas. But now finally, we're getting to the good stuff in chapter 5. We're going to start modeling data using the normal model or the normal distribution. Any questions at all before we go to the next section? Okay, these next two sections are longer, I'd say. So we will probably be doing quite a bit of next week in section 5.2, or excuse me, section 5.3, section 5.4. Section 5.5 is optional. We won't be covering it, but it's a good read if you just have extra time. If you need just some material to help you go to sleep at night, that could get you there. So let's close this up. And now we're in section 5.3, the normal models. Okay, so starts off with some interesting graphics. And we have an empirical rule or the 68, 95, 99.7 rule right out of the gate. Sometimes our author goes by that rule. Sometimes he just abbreviates by saying empirical rule. I'll try to say this more often because that's a good name. The name of the rule also conveys the formula at the same time. So it's pretty helpful. So what's going on with this? We're trying to deal with the data distribution. So think histograms for one quantitative variable again. We want something that is obviously unimodal and at least roughly symmetric. If those two conditions hold, then we can take a look at all of the data we got. Think of some of those problems that had 20 observations or even more. We can say approximately 68% of the observations are within one standard deviation of the mean. As a picture, this is what it looks like. The mean goes here. If you subtract one standard deviation from the left, one standard deviation for the right, we have 34% on the left, 34% on the right in this, I guess that's a purple region, kind of a pastel color. That's the 68% in the rule so far. So what are we looking at, by the way? This is just some weird curve, but this is the normal model. And sometimes we call this the normal distribution. In fact, if you look at the DISTR in your calculator right here by bars, that's what it's talking about, distributions, like the normal distribution. So those are completely synonymous. I might say one or the other. So the next part of the rule says approximately 95% of all your observations, all of your quantitative values from your data should be within 2 standard deviations of the mean. Let's pause on this part right here. 2 standard deviations is pretty far away. It's going to go from out here. I'm not sure if I like how I conveyed that. It's going to go from here to here on the 2 standard deviations. We're claiming that's 95%. And look at these percentages. If that's accurate, it should add up to directly 95%. We might as well verify it, see how it goes. So take 13.5 times 2. Add to it 34 times 2, or just 68. That's what it would add up to. And we get the 95%. So this is saying 2 standard deviations is really far out. If you have a quantitative variable and produce a histogram out of it, which is unimodal, at least roughly symmetric, it's essentially saying almost all of your data is within 2 standard deviations. Anything that's outside of that is pretty unusual for your data set. Then it gets even more extreme. We mentioned before, 2 standard deviations are a lot, but 3 standard deviations is becoming exceptional. And by the empirical rule, that looks like the case. It's saying if you go 3 standard deviations out, so now you're from here all the way out to here, that should be 99.7% of all of your observations. It's approximate, so the more skewed this is, the less accurate it'll be. But the more and more you have symmetric, mound-shaped unimodal data, the closer that is going to be to actually true each and every time. That's kind of impressive. But one thing that we might want to add to this diagram is, well, we do know if we add up all those numbers, we should get 99.7. Let's verify that just to make sure the numbers are right. We have 2.35, but notice the total symmetry in this curve. 2.35 mirrors over here, so put in 2.35, double it. Same with this one, 13.5. Double that one. And then add the middle, which is 68. Comes out as 99.7, and that's kind of interesting, because if we're talking percentages, where's the rest, right? This curve is really, really crazy in a certain sense. There's a mathematical formula to give this curve. We'll see it in section 5.4. The one key fact about this curve is it goes to the left forever, unstopping. It never actually even hits the x-axis. So there's always a separation of the curve. It's approaching the x-axis rapidly, but never even touches it. There's actual area to the left. There's area to the right, and we need to find that area. So let's do it. If it's 99.7% going from here to here, we can say that the 2 missing tails, that's in this region and in this region, should be 100 minus 99.7. So that's the missing part, 0.3%. Also, there's total symmetry. The area here is the same as the area here. So if you divide that by 2, you get the missing numbers. 0.15% goes here as well as out here. So let's fill that in. So this is 0.15%. I'll just put a little arrow pointed there to convey it's in that far left tail, 0.15%. A little arrow that goes here, and I think I said far right tail. That's the far left one, and this one is the far right tail. So that's our complete diagram. It all comes from the empirical rule right here. But there's conditions when you're using this. It's already kind of stated up here, but this is what the book calls nearly normal condition. It's his way of admitting that no data is perfect. Perfectly symmetrical data is a mathematical fiction, essentially, almost as an indication of fraud somewhere if your data is perfectly symmetric. The condition says the shape of the data's distribution is unimodal and at least roughly symmetric. and there are no obvious outliers. This is the condition required in order to model data using the normal model. So we'll have to check this condition by just examining a histogram. One of the reasons why we looked at histograms so often in chapter 2. So what we're doing is checking the nearly normal condition on the examples below. Any questions first, folks, about the normal distribution here? Okay, scrolling down, here's our first example in these notes. Example 1 says, a veterinary anatomist, that sounds like a pretty cool job, by the way, probably lots of school for that, investigated the spatial arrangement of the nerve cells in the intestine of a pony, probably a sick pony. So got brought into a specialist and there took probably a sample and put it under a slide. And now we're looking at the nerve cells in that intestine of a pony. That sounds morbid, but they're helping the pony. So let's keep on going. He removed a block of tissue from the intestinal wall. So he has, imagine just a small square of meat, probably a sugar cube size, cut the block into many equal sections, and counted the number of nerve cells in each of the 23 randomly selected sections. That sounds like he has a ton of assistants and a big lab to actually do this. That's labor intensive. A histogram of these data is provided below. So let's look at the histogram. So when you see this, this is saying, for example, that in this region, there were 7 blocks of that original chunk from the intestinal wall that had between 25 and 30 nerve cells. So that's what this histogram right here is conveying. So now we have to decide on part A, this is a single part problem. Is it reasonable to model these data using the nearly normal condition? Using the normal distribution? Well, first we have to decide, is it at least roughly symmetric? Would you say yay or nay to that? There's a touch of left skew to there, I would agree. But no data is perfect. Even though there's a touch of left skew, it would still fall into at least roughly symmetric.
You still have the hump, right?
We're definitely unimodal, absolutely. But here's another way to think about it. What we're trying to do is use the empirical rule, the 68, 95, 99.7 rule, which means we're trying to fit a curve on top of the histogram to model all the data. Why would we do that? Well, it's not about that one single chunk from the intestinal wall. We wonder what would happen to all of the intestines if we repeated this over and over again. So we're trying to model a population with this curve, just using the sample data. We try to put a curve on it, it would look about like this. Left skew for sure, so it's going to be imperfect, but the peak of my curve should be right around the peak of the data, and then it has to come down like this in a totally symmetric way. Not perfect at all, but this would do the job actually. Let me try if I can see if I can do a little bit better. So my curve should come up, around and down like that. Definitely it's not perfect. If it was a nice perfect histogram right here, you wouldn't see this white space at all. In fact, just for the sake of emphasis, let's see if we can find something that had really close to perfect symmetry from an old problem and do this again. It would have been somewhere in, starting to get kind of, yeah, probably in here. It's starting to get foggy where these were. That looks about right. So this would be like the world's best data. You would almost never see data as nice as this if it's real data. If you put a curve on this, it would look about like that. Not even this is perfect, but this looks like it is definitely going to satisfy the nearly normal condition. You can model this data very well with a normal curve. But back to this one, it's not perfect, but you can still make some decent approximations using the 68, 95, 99.7 rule. So I would say for this problem right here, we could say, since the histogram is unimodal, and let me see if I can get more space. I always feel I can put it in this one spot, but then when you do it in class, you realize there's not enough space for these things. Let me just see if I can make this a little bit nicer on the notes without trying to cram it in. So back to the histogram, we can say, since the histogram is unimodal and mostly symmetric, it has that slight left skew, but that's not enough to make the condition not work. We can say the nearly normal condition is satisfied, and so we can use a normal, you could say normal distribution or normal model, however you'd like to say it. Let's go with normal model. So again, this is not ideal, but this would work pretty well if you try to model the data with the 68, 95, 99.7 rule. Any questions at all, folks, with this display here? Okay, so the next one is going to be definitely a case where it does not work, very flat, plainly can't work, and that's part B. We actually looked at these data before in a prior section. I forget what the section was. This is the 2015 Urban Mobility Scorecard from the Texas A&M Transportation Institute. So this is the estimated cost in millions of dollars resulting from wasting time due to traffic congestion and other problems. And this is the 13 largest US urban areas that have a population over 3 million. The other problem actually had the data table, but this is just the histogram. Question on this one is it reasonable to use the model to model these using a normal distribution? Would you folks say yay or nay? Yeah, this is looking pretty bad, right? It is unimodal, so that's got something going for it, but it's terribly, well, not terribly, but highly skewed to the right. We try to put a normal curve to it. Well, the peak of the curve has to go up right around here, and it has to be symmetric, so it would look like this. Something like that, and then it has to come down for the rest of the data. But that looks like it's not doing a good job at all because all of this white space on the left suddenly doesn't even make sense anymore. You're predicting stuff on the normal model that doesn't even have values going to the left of 2. Here, there's an imbalance problem for sure, but at least on the extents of the curve, we do have data on the left and the right, so it's not as, well, skewed. So this is a terrible distribution to use a normal model on. There are other probability models, but we can't use the normal distribution for this one. So let's say here, we cannot use our normal distribution to model the data since it is highly skewed to the right with, this is another problem with the normal model. Outliers can also throw it off, and we definitely are looking at some potential ones. So we'll say with potential outliers. So that's the 2 different kind of cases. This one is a big fail for the normal model. We can't model using the normal distribution at all, but we're pretty forgiving even when the data is imperfect. This one's skewed left, but it would still be modeled pretty well with that distribution. Any questions, folks, with looking at those histograms again? Okay, Elisa answers the question of why did we care about histograms so much is for these kinds of things. And the normal distribution is a pretty amazing distribution. You might have heard in other contexts that lots of things are modeled normally. If you look at, say, all the heights of children in the 5th grade, for example, put them in a histogram and it's going to be symmetric. You could use a normal distribution to describe it. But the purpose of the normal model goes way beyond that. It turns out, for reasons that are really complicated that we're going to take a look into, even if your data is skewed, if you're doing things like doing a confidence interval or hypothesis testing, with a large enough sample size, you can still use the normal model in the right context, just not in this situation. So the normal model is tremendously flexible, it turns out. And that's why a calculator like this, if you go turn it on, hit second, and then bars, you see normal PDF. That gives you the points on the curve. Normal CDF, that gives you areas in here that you can convert to percentages. And inverse norm gives you the values on the x-axis. We're going to see how all that goes in section 5.4. So think of 5.3 as we're just trying to get used to what is the picture in your mind's eye whenever you use these three functions right here. That's the picture. And without having the picture, your calculator turns into just some random black box that accepts a number, gives some other number out with no intuition. That's always really dangerous in statistics because statistics are hard enough on their own. So here's the normal model again, and the empirical rule as well. So the normal model is this right here, or normal distribution. It's a family of curves that models unimodal, at least roughly symmetric data, but it has an abbreviation. Sometimes, instead of saying the normal distribution with mean, whatever that is, standard deviation, whatever that is, we say n, mu, sigma. And this is just a shorthand to say we're referring to the normal model where mu and sigma are a new word, parameters. I might have slipped that word in here or there, but we're now finally formally defining it. What is a parameter? A parameter is something that describes the population. So mu is the population mean, not the sample mean like we've been saying before. To get a population mean, you have to contact every single member of the population and do a measurement. Then do your statistics on all of the data. That means you have a census, and that's often so expensive that it's almost never done. You have to even question the US Census. That's a big deal, right? How accurate is that as a census as well is up to debate. We can't say with 100% certainty that every single American was actually contacted by the US Census, even though we do the best job to make that happen. So even our national census is suspect to be not a fully accurate census on its own. Likewise, sigma is the population standard deviation. So this can be paraphrased by saying up here, the normal model with mean, mu. If we're using mu, we're talking about modeling the population with that entire value, and standard deviation, sigma. Oh, by the way, we might as well add on this diagram here, 0.15%. It's just handy to have it, 0.15% here as well. So I won't use that shortcut all the time, but it's a handy one to be aware of. Our author uses it a lot as well. And if we are talking about the standard normal model, it's referred to as N01. This would mean if you see N01, let's write this out here, that the mean mu is 0. So the population mean is always the first input in that notation. It would also mean that the standard deviation sigma is 1. So the population's standard deviation is always the second value there. Any questions, folks, with that brand new notation? It is quite a bit, yeah. Any other comments so far?
Standard deviation.
Oh, this one right here?
Yeah.
Oh, gotcha. This one is lowercase sigma, like there's uppercase sigma as well, all sorts of things going on. But this one is sigma. And this one right here, mu. We learn a lot of Greek when you're taking a statistics class. And I'm glad you mentioned that. By the way, if you're trying to write mu, it's almost like you're doing the letter U, but you start with a tail going out like that, and then make your U. It's kind of weird.
Yeah.
Oh yeah, that's unfortunate. You're kind of doing Greek a little bit, I guess, is what that's saying. That's okay. As far as sigma goes, imagine you're doing the letter O, but then you just give that one a little tail going off like that. You've got a sigma. Yeah, kind of, yeah, that's a good way to think of it. So far, we've just been talking about the normal model, the empirical rule, and when we can use the normal model and the empirical rule together. But example two, this might be our last one for the day. We're going to actually use it to good use to make predictions. Any questions at all first, folks? Okay, so this is what the homework questions look like in this section 5.3. Again, by the way, if you do homework a little bit early, there might be some questions that are a little bit tricky there since we're not completely finalizing these notes until Monday's class is over. But here's the situation here now on example two. It says the time it takes a driver to react to the brake lights on a deaccelerating vehicle is critical to helping avoid rear end collisions. So I think that's just a statement of fact, right? It's kind of a weird thing to say, but it just puts us in the context of what we're dealing with is why they said that. The article, Fast Rise Brake Lamp as Collision Prevention Device. I don't know what a fast rise brake lamp is, but you never have to actually look into these articles. I just post them here just if you're curious. This is old data. Suggests that the reaction time for an in-traffic response to a brake signal from a standard brake light can be modeled with a normal model, or excuse me, normal distribution or normal model. Let's pause right here. He's saying the time it takes to react when you see someone is braking in front of you, essentially, can be modeled with a normal distribution, having a mean value, 1.31 seconds, and a standard deviation of 0.42 seconds. Still don't know what that is about, so we're only looking at one aspect of the article, the statistics mainly. Excuse me, I misspoke. Those are not statistics any longer. What we're doing with these things is we're trying to model the entire population of drivers responding to brake lights with that value. Mu equals 1.31 seconds. Now, is that accurate? Probably not, but we're trying to model data. We're modeling a population of all the brake times that it will take that you could possibly get, with this as the best guess as the mean of the population. We're not saying it's exactly that value. In most cases, these are always unknowns, and we just have approximations. But we're using mu because we're treating this as a parameter. We're describing the population now. Likewise, if we're saying we're going to be modeling with a normal model, these things are parameters, and now we use sigma equals 0.42 seconds. Absolutely. Well, let's add that comment here that the reason we're not using X bar and we're not using S is because we're modeling a population. Here, we're going back to parameters. The parameters describe a population and
sample of the population.
Exactly. Yes, exactly. And we'll come back to that down here because that's honestly confusing. So we'll come back to statistic versus parameter and talk a little bit about census as well, because we've been doing this all along with sample data. Now we're dealing with the parameters instead. Other questions so far? Okay, so just let's add this extra comment. Since we are modeling a population, these are parameters. Not the statistics. X bar S. So that's a little bit weird, but part A says state the value of the parameters. I think I gave it away. It's these two right here. So let me just take this off to convey what we should have put here. So I got a little excited when I found the parameters. Part A says state the values of the parameters, and they're these two. Mu equals 1.31 seconds, and sigma equals 0.42 0.42 seconds. So those are our two parameter values. Next thing we're going to do is draw the normal model for this population. When you go to do this in MyStats Lab, it's multiple choice, which is kind of weird. But again, think of MyStats Lab as it's just practice before you do it again as a quiz, before you do it again as an exam. Because of that, when you do these problems in MyStats Lab, I encourage you to just draw it out like you're doing a quiz problem or exam problem. That'll help you way more than if you just analyze the multiple choice. So we're now drawing the normal model for the population with those two parameters.
Go back to the little note and change X bar to Y bar.
Oh yeah, thank you for that. That's a terrible omission on my part. I mean, I like that the calculator says X bar, so it makes it seem legitimate. But it's good to have some parallelism through the notes. I appreciate that. Other questions at the moment? Okay, so coming down below, to draw the normal model, I want to emphasize your drawing doesn't have to be perfect, but there's a certain couple things that we have to have there. So I'll mention those below after we do the drawing. There's two things we're going to do. First, we draw the model, then we'll label it. So we're focusing on the drawing first. I would start with a really long horizontal bar. Think of it as the x-axis from a math class. The axis here actually has a unit. The unit is going to be inherited from these values. It's seconds. It's seconds to react to a brake light, specifically. So let's put in that description. Seconds to react to a brake light. So that's always the first step. Just draw your axis. I wouldn't take off points if you didn't put the unit in, but it will absolutely help with the follow-up questions. It gets us in the context of what's going on next. Now we are going to try to draw the normal model. I'm going to draw incorrectly first. We should never draw it this way. Not because the drawing is bad, but it's because the normal model should really look like this. It has to always be above the x-axis. Exactly, it doesn't even touch it, which is kind of amazing. So I usually start off on the left, kind of close. Let it gently increase, then suddenly rapidly. Oh, kind of a little weird there. Then let it sort of gently taper off like that. That's not my best normal model. It kind of looks a little bit weird, got a shaky hand, but that's okay. If yours looks even worse than that, all you're trying to do is convey information to one spot. So the only thing that you could possibly lose a point on is that, that looks like that. So make it look like it's always above the x-axis and you're in good shape. If it looks like it's barely touching, I'm not super picky about that. So that wouldn't be a problem. Next thing we do is we put the mean in the middle, corresponding to the peak. So right here, 1.31. Now we're going to start adding standard deviations. Because of the 68, 95, 99.7 rule has a statement about one deviation, two standard deviations, and three, we want to go 1, 2, 3 tick marks to the right, 1, 2, 3 tick marks to the left. Now it's a calculator problem at this stage. You're going to take 1 point, let me get out of here first.
Get there.
On the calculator, I should just be on this blank screen right here. Oh. Yeah, just doing the 1.31. Then go plus, we're going to do the upper end, and add 0.42. So that's what your calculator would look like at the first step. Yeah, so that's just one standard deviation away, 1.73 seconds. Now always remember what these values mean. That means the person, say behind you, when you hit your brake light, took 1.73 seconds to respond to that and actually hit their brake light. That's within one standard deviation, so that's typical. That's kind of awful when you start to think about this. Let's keep on going.
So then we add another.
Exactly. Adding another could be just times 2. Or you could go like this, plus 0.42. Oh, hang on, my dyslexia is showing up. 0.42. And it's going to add it to the prior value. So either way you like to calculate it would work out just fine. So 2 standard deviations is 2.15 seconds. That's atypical. 2 standard deviations is far away. Add 0.42 again. That's 3 standard deviations over 2.5 seconds. That just sounds like a rear end collision at that point. Depends on the speeds, of course, but 2.57 seconds. But again, 3 standard deviations is outrageously far out there for data. Then we just go in the backwards direction. Exactly, start by putting in 1.31, subtract, and just the standard deviation again, 0.42. So 0.89 seconds. So that's 1 standard deviation on the lower end. So these are people with fast reaction times. These are the people who won't get you into a fender bender. To get for the next value, just go minus, again, 0.42. These are people who had lots of caffeine or something, less than a half a second to react, but that's 2 standard deviations. That's abnormal. These are high reaction time people. And now we get to a weird part of our model, 0.05 seconds. That person is either like maybe a pro gamer of some kind, just immediately responding to whatever signal they see, or the model is imperfect. That's probably what's more likely. The values you see here are not always going to match reality 100%. We're modeling reality just to the best of our ability. Oh, that's possible, yeah. They could be seeing patterns, that's possible.
I actually was watching the part and I could see.
That's just survival sometimes. Yeah, for sure, yeah. So we did it, folks. We drew the normal model. And when it says clearly labeling it, showing the rule, pretty much this is all we're going for. Remember this diagram right here? We're just putting in the percentages. So let me scroll down and see how well I remember those. If you wanted to, you could just go here, here, and put 68% in the middle if you'd like. But you might notice it would be, yeah, through the 68, 95, 98.7 rule. What's not always the same is how accurate it's going to be. Probably not terribly accurate on this one. I would think it's probably better to actually break it up, go 34%. 34%. Because the questions about this kind of problem line up with the tick marks. So it's just good to have that region laid out. Then go 1 left, 1 right. This is 13.5%. 13.5% again. Here on the next tail, it's I think it's 35%, but I'm forgetting. Let me double check on that. 2.35%. That's a bad one to misquote. Again, over here, 2.35%. This would be good enough for me, but again, sometimes with the problems, the way the questions are asked, it's good to go a little bit further. So let's go beyond. Go 0.15% on the farthest left tail, 0.15% on the furthest right tail. So that's the whole model, folks. Any questions at the moment? Okay, now that we have that, we can answer a whole bunch of follow-up questions about this, but I'm noticing that took a lot of time. We have like a minute and some change. Probably a good stopping point for us right here. We'll do this again when we come back on Monday with the next question, building a normal model like this one. But any last questions or comments, folks, on where the notes are ending here? Okay, well, have a great weekend, folks. Try not to work too hard. And again, I'll have the results posted on Moodle, but I'll message the whole class on the announcements forum when the grades are posted.
Usually when you post the grades, it tells us you did.
Oh, it does. I actually didn't know that. So
Yeah.
that's good information for me.
So like when you post the grade, it said you have made a.
Okay,
comment.
I see. I never actually knew that. Thanks for telling me.
It does. You don't have to tell everybody.
I learned the most about Moodle just for comments like that. For example, someone told me that if you put a due date here, it just makes Moodle more reasonable because you can actually see everything that's due.
Yeah.
I didn't do due dates for the longest time until just someone told me that. So I appreciate that.
Yeah, no, that has made my life easier.
Awesome.
Yeah, as soon as you put something in, it'll just say, let's see what we think. Yeah, I get an email from them saying, hey, This person commented on.
Thank you.
I got one the other day.
Oh my gosh, 4 almost earned that.
Oh, it just says, your teacher has given feedback for an assignment submission exam. one,
I see.
or whatever. Even if you don't
Cool.
comment on it, as long as you submit it or whatever, you grade it, then that'll be it.
Gotcha.
And anytime we submit something on Moodle, it'll email us that we submitted it. Yeah.
That's weird. That's a little
Yeah,
bit
it's kind of
redundant.
annoying.
Huh,
We get a lot of emails,
that's
but
terrible.
yeah.